Welcome to the first video lecture. The course ID is CET302 and the course title is Structural Analysis 2. And in this video lecture and in the upcoming lectures, we will be learning about the introduction to the matrix methods. So the matrix methods are used for solving the structures. It includes the analyzing the reactions of the structure. It can be a frame, it can be a beam, and also analyzing the bending moment, shear force, etc. that is resulting in a structure due to the action of the loads. So the contents of this lecture are the matrix analysis of structures, definition of flexibility and the stiffness influence coefficient, the concepts of physical approach. Then next one will be the flexibility method, the flexibility matrices for truss and frame elements, like how to develop it, and the load transformation matrix and development of the total flexibility matrix of the structure. Then the problems of analyzing the simple structures like the plain truss, plain frame, nodal load and the element load, lack of fit and the temperature effects. So in this a series of videos we will be learning only how to frame the matrix for a structure, and the detailed analysis will be done in the upcoming lectures. So basically there are two methods for solving a structure. It is first one, force method, and second one, displacement method. So this is actually the core of this matrix analysis of structures. So in the case of flexibility method, it is also called as the force method. The actions are the primary unknowns. So we don't know the reactions and also the forces. So these methods are applicable to discretized structures of all types, and to analyze by this force method, the actions are the primary unknowns, which the action means they are the considerable unknowns which will create the deflections in a structure. Okay, so these are the loads which are acting on the structure. And the static indeterminacy, it is we already know the definition. It is the excess of the unknown actions than the available number of equations of the static equilibrium. So the other approach will be the displacement method, which is also called as the stiffness method, in which the displacements of the joints are the primary unknowns. So this is the main difference. The previous one, the actions are the primary unknowns. In the stiffness method, displacements are the primary unknowns. And in displacement method, we are more focused on the kinematic indeterminacy in place of the static indeterminacy for the force method. The kinematic indeterminacy is defined as the number of independent translations and rotations and the unknown joint displacement, and these are more suitable for the computer programming. So the START software which you will be studying during your course is based on the displacement method or the stiffness method. Okay, so let's have a look at various structures and their actions first. So the there are different types of frame structures. Like the A, it is a beams. So normally the beams are supposed to carry the loads, and it will take the load by undergoing bending moment, shear force, and the axial force. The axial force, even it will be very less compared to the bending moment and the shear force. So these are the picture. The A, it is a picture showing a beam acted upon by different load, incline load, a point load, as well as a moment, UDL, incline load, etc. In the case of plane truss, so always you know that the truss is supposed to carry only the axial load, and as being a plane truss, it is having geometry only in two dimension like x and y, and always joints will be hinged. It is one of the assumptions of the truss analysis, and generally only the axial forces are the main forces in the truss member. It cannot and never support twisting moments. In the case of space truss, it's an extended version of the plane truss, where the geometry is available in the three dimensions. There will be an Z dimension also, and here also all the joints will be hinged, and it is also supposed to carry only the axial forces coming on the individual members. But even a truss member can have some bending moment and shear force if the loads are directly acting on them. But normally we will prevent the happening of the bending moment and the shear force to the truss. Always design such that it will have only the axial forces. So the C shows a space truss. Yeah, the B was a plane truss. Plane frame, same like it is a two-dimensional. Here the difference is all the joints are rigid. So the difference between trusses and the frames is in the connection. Basically here the frames, all the joints are rigid, which are capable of taking the bending moment, and all the forces in the plane of the frame, all the couples with their vectors normal to the plane of the frame. So all the forces and the bending moment, shear force, all acts in the plane of the frame. The next one is the grid. The grid you can relate with the like the beam and the slab arrangement. Here all the forces, it means the live load, dead load, etc., when it's transferred through the slab to the beam, it is actually simply represent a grid. All the forces normal to the plane of the grid, all couples with their vectors in the plane of the grid. It includes the bending and torsion which can happen to the individual beams. Okay, like you can idealize as a slab. From this slab, the loads are transferred to the beams. Yeah. So in the case of space frame shown in F, it is actually extending to all the dimension X, Y, and Z, and it is like the 3D building, but we see all are assembled of the space frame, and it is always the ends are hinged, and the bending moment, shear force, axial force, torsion, everything will comes into play when we are dealing with the space frame. Generally, the deformations in a frame structure can be taken as in different direction, like the X, Y, and Z. Basically it is due to three forces. First is nx. Nx will be the considering x direction, y direction, vertical, and this is perpendicular to the plane. The nx is the axial force in the direction of x. Then like there is this Fvy, which is a shear force which is acting in the direction of the y. Vz is there acting in the direction of z. And also there are three couples, that is the moments, which is tx, my and mz. So tx is in the direction of the z, which is acting like this. Yeah, it will be in this direction. My will be with respect to, it is actually about the y, and the tx will be about the x, and mz will be about the z. So these are the different forces that acts on a structure or an individual element. And the types of deformations in frame structure, it can be the axial force, it can be the shear force, it can be the flexure, and also it can be the torsional, which will twist this element. So summarizing the different deformations happening in the structure, the beam always taking the flexural load, the plane truss and the space truss will take the axial load, the plane frame will take flexural and axial, and in the case of grids it will take the flexural and the torsional. The space frame will take the axial, flexural and torsional deformations. Now there are some slides on finding the static indeterminacy. You know the basics of this one, and just a quick recap. So for the beam, the static indeterminacy is equal to the total reaction component minus the number of equations available. So you can find for the different beams, like single span beam with both and hinges, with inclined load, continuous beam, proper cantilever, fixed beam. These are the various type of beams based on the support conditions. And as an example, for an inclined simply supported beam with an inclined force, the static indeterminacy is actually 0, because you could find the reactions at the left support and the right support by using the simply equations like sigma h equal to 0, sigma b is equal to 0, and sigma m is equal to 0. In the case of an additional support, here actually 3 supports are there, and there are 2 unknowns. So here, being the force inclined, there will be 2 vertical reaction as well as a horizontal reaction for this one. So 2, then here 1, only vertical, here 1. So 2 plus 1 plus 1 will be the 4 unknowns, minus 3 equations will give you the 1 indeterminacy. Here due to the inclined force, this inclined force will create 2 reaction. For this hinge support, there will be horizontal reaction and the vertical reaction. So there are actually 2 unknowns at left support and 1 unknown vertical reaction at the right support. So 3 unknowns, 3 equilibrium equations, so it can be solved. So there is no static indeterminacy. In the case of a fixed beam, there are 3 unknowns at the left support, 3 unknowns at the right support. So 6 unknowns minus 3 equilibrium equations will give you the static indeterminacy as 3. Coming to the rigid frame, in the case of a rigid frame, so we have discussed rigid frame. In this one, all the forces and the bending moment, shear force, all will be in a single plane, and all the joints will be rigid. For finding the total indeterminacy, it is actually a combination of the external indeterminacy plus the internal indeterminacy. So external indeterminacy is equal to, is actually calculated like the previous one. It is total unknown reactions minus 3, which are the basic equilibrium equations, will give you the external indeterminacy, and the internal indeterminacy is equal to 3 into number of closed frames. Okay, so the total will be external plus internal, r minus 3 plus 3a. Please note that always an additional hinge will, so an internal hinge will provide an additional equation. So these are examples. So total is equal to external plus internal. External is equal to r minus 3 plus internal is equal to 3 into a. Here two unknowns here, horizontal, vertical, two unknowns here. So total 4 unknowns, 4, 2 into 4 minus 3 plus 3 into 0. There is no closed frame. Here t is equal to e plus I. So here being fixed 3 unknowns, 3 unknowns, 3 unknowns. So total 3 into 3, 9 unknowns minus 3 equilibrium equations plus 3 into 2, because A is actually 2 here. This is a one closed frame, a second closed frame. So 12. Here one unknown, sorry, 2 unknowns here, 2 unknowns here, 2 unknowns here. 3 into 2, 6 minus 3 plus one closed frame, second closed frame, third closed frame. 3 into 3, 12. Here totally 1, 2, 3, 4. 4 into 3 unknowns, 12 unknowns minus 3 equations plus 1, 2, 3, 4 closed frames will give you total 21. So for this one, here you have 3 unknowns here. So total 6 minus 3 will be 3 external indeterminacy and internal indeterminacy equal to 0. So 3. So this is actually exercise. If you calculate, you will get 63 will be the static indeterminacy. For this one, actually external will be 3 here, 3 here, 3 here, 3 here. 12 minus 3 will be 9 plus internal indeterminacy will be 63 minus 9, which you want to find from this one. Okay, like this for the space rigid frame, the total indeterminacy is the addition, can calculated by the addition of the external plus the internal, but not that E is equal to external is equal to r minus 6, because being in space you have 6 equilibrium equations in 3 linear and 3 rotational. So r minus 6 will be the external indeterminacy and internal will be like 6 into closed frames. Previously it was 3 into closed frames. So for this example, t is equal to e plus I is equal to r minus 6 plus 6 into a. So here for this one, suppose there are 6 unknowns in space, 6 unknowns in space, 6, 6. So 4 into 6 will be 24 minus 6 plus 6 into, so this is treated as a single closed frame. So 6 into 1 is equal to 24. Then for the case of plain truss, generally the external indeterminacy equal to is equal to r minus 3, which is same as for the plain frame, and the internal indeterminacy is found by m is equal to 2j minus 3. Here minimum 3 members and 3 joints are required for finding the, or for making a truss. At least you need a 3 member and 3 joints will be there, and any additional joint requires 2 additional members. Hence the number of members for stability is equal to m equal to 2j minus 3. So m minus 2j minus 3 will be the internal indeterminacy. Yeah, so total will be the external r minus 3 plus m minus 2j minus 3. So solving m plus r minus 2j, where m is the number of the members in the plain truss, r will be the number of reaction components, and j will be the number of joints. Here also the provision of internal hinge will provide an additional equation. Secure some problems. Total is equal to, so the final equation is m plus r minus 2j. So m will be number of members here. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 plus 3. That is 2 unknowns here, 1 unknown here, being a roller. So 3 will be in that way. Yeah, so 9, 3 will be the r value, and minus 2 into j, 2 into 6. So 1, 2, 3, 4, 5, 6 joints. So this equation is satisfied, and we will be getting the SCN is equal to R minus. This is actually an subdivision. You can directly find with this equation. So SCN is equal to 0. Also the internal is equal to 0. A second example, T is equal to M plus R minus 2J. So members will be 1, 2, 3, 4, 5, 6, then 7, 8, 9, 10, 11, 12, 13, 14, yeah, 15 also there. So 15. So 15 members are there, plus so two unknowns here, so 4 minus 2 into 8. So there are 1, 2, 3, 4, 5, 6, 7, 8. 8 number of joins will give you the values total indeterminacy. So we know SCN is equal to this, and internal is equal to T minus E will give you 2. Similarly, you can solve for the example 3 also. So example 4 also can be similarly solved. Example 5 and example 6. So in the case of a wall or roof attached pin jointed plane truss, so this is a wall and this is a roof attached. In this case, the internal indeterminacy is equal to M minus 2J, and the external indeterminacy is equal to 0, since once the member forces are determined, the reactions are determinable. So here directly the T is equal to I is equal to, because E is 0, M minus 2J direct equation, M minus 2J, M minus 2J. You can count the number of members, you can count the number of joints to find the values. Here 1, 2, 3, 4, 5, 6 members, minus 2 into 3. So there will be 3 joints. Joint 1, joint 2, and joint 3. Similarly, you can solve for the example 2 and the example 3. In the case of the space truss, the external indeterminacy is equal to reaction components minus number of equations available. You know, for the space 6 equations are available. Sigma V equal to 0, sigma H equal to 0, like sigma in the direction of Z is equal to 0, and all the moment in all the 3 directions are equal to 0. Yeah. So total in external and internal indeterminacy is equal to T plus M plus R minus 3J. And for this one example, you need to count the number of members correctly to solve this one. So the member, if you count the total members in this space truss, it will be 12, and the R will be actually 9, being 2 here, 2 here, 2 here, 2 here, 2 here, 2 here. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Just a minute. The reason is that for the hinge, for this one, it won't allow it will have a vertical reaction as well as a horizontal reaction. So there will be 2, 4. Yeah, 2, 4 here, 2, 4 here, 2, 4 here, and this will be having only 1. Okay. So the value 9 and minus 3 into 6, j number of joints will be 6, will give you the value of the E. And so we are now going to study in detail on the actions and the displacement terms which we have discussed in the first slides. So the actions, they are always the external actions, and it can be the force or a couple or combination. So it can be a moment, it can be an axial force, or it can be a combination of the force and the moment. There can be also the internal actions which are the resultant to this external action, which are called as a stress resultant, which is the bending moment, shear force, axial force, twisting moment, which will happen due to the actions of the external force. And in the case of displacement, it is always termed as a translation or rotation at some point. Displacement is always accompanied due to an action. When there is a force, then only the structure will deform. So need not be the displacement caused by that action. So in detail, the external actions in this figure are the P, it's a cantilever beam with a free end load. So the free end, there's an axial force or vertical force P1, and there is a moment M1. So the external actions are P1 and M1. So in this one, the after the application of P1 and M1, we can find that there will be a vertical displacement which is taken as delta, and definitely there will be an angular change which is taken as theta. So this delta and theta are due to the combined actions of P1 and the M1. So displacement correspond to P1 is delta, but even this is actually caused by both P1 and M1, and displacement corresponding to M1 is theta, because M1 is actually trying to rotate the beam, which will create a theta, but definitely the theta will have some effect from the P1 also. And now we are going to study some notations for the actions and the displacement. So always the actions are denoted by A, and the displacements are denoted by the D. Okay, so this is actually a proper not a proper cantilever, it's a simple cantilever, being a free end, and it's acted by the A1 load. A1 is a vertical load, A2 is a vertical load at the free end, and A3 is a moment. So these are the A1, A2 and A3 are the actions on the structure, and due to this action there is a deflection D1 at below the load point A1. Below the load point A2 there is D2 deformation, and definitely due to this moment there is a D3 also. So these are the length of this beam, L by 2, L by 2. Okay, so we are splitting the beam into two. Sorry, not splitting the beam into two, we are actually splitting this full beam in action wise. That is, in the first figure only A1 is there. So here please note that always this D1, D2 and D3 has got some influence from the A1, A2 and A3. That is, the D1 is not only due to A1, there will be a contribution from A2 as well as A3 also. So when we are considering only the A1, so A1 is applied, we are removing all the forces A2 and A3 here, and when we draw there will be a displacement D1. There will definitely, even we are loading here and there is displacement here, but displacement will keep on continuing, and the end also there will be a deflection. There will be definitely a twist also with respect to the horizontal, there will be an angle. So D11 means it is the displacement at the first position due to the load at the first position. So first one, D11, the first one will be the location and the second one will be the cause. Okay, so D21 will be the displacement at the second position due to the action 1. D31 will be the displacement at the third position due to the force A1. Similarly, for the A2, please note that all the effect, like the second one will be 2 because it is happened due to the A2, and the first one denotes the position 1, 2 and 3, and for A3 also like the 3 will be the second number which tells that the A3 is due to the A3, and the first one will represent the positions. These are the equilibrium equations. The resultant of all forces, a force, a couple or both, must vanish for the static equilibrium. The resultant force must be 0. Sigma Fs is equal to 0, sigma Fi 0, sigma Fsl 0. So these are the equilibrium equations for a space frame, and for the space truss as well as for the space frame. Sorry, for the plane truss as well as for the plane frame, we have being a two-dimensional problem, we have 3 equations of equilibrium: sigma Fs 0, sigma Fi 0, sigma Mz 0. And in the stiffness method, the basic equations to be solved are the equilibrium conditions at the joints. So next important term is the compatibility. Compatibility, by definition, it is the conditions of continuity of displacement throughout structure. So all the displacements in a structure should be continuous. That is, example is at a rigid connection between two members, the displacement, that is translation and rotations of both members, must be the same. That means suppose you have a rigid frame, and upon the action of a load, if the beam is bent like this means that the total deflection, there is always this 90-degree angle is maintained, and how much it is actually inclined for this column will be there for the beam also. So the total, there should be compatibility between the deformations at every joint. In the flexibility method, the basic equations to be solved are the compatibility condition. Okay, so we will consider the next slides in the upcoming class.